Hello students, a very good evening.
Good evening, sir.
Good evening, Amrita. So students, today we are going to learn, what are the main brain of the circuit which we are going to learn. So whatever the chips we are manufacturing, what are the chips we have, there is a brain for every chip. So there's nothing but the FSM, the finite state machines. So we will go through that. So how many types of FSMs are there? So what is the necessity of the FSM? And how FSM can detect the sequence like that. Let me share my screen. Hope my screen is visible to all. Fine. So students, today we are going to learn about finite state machines. It's the main brain of every digital circuit. Every chip has almost every chips, whatever we are learning, whatever we are working on, every chip it contain FSMs. So they are actually mainly classified into two types, Moore and Mealy. So we are going to cover some theory part applications, and we are going to detect 1000 sequence. So there are so many ways to detect, but there are so many coding styles also. So we are going to learn one of the coding style. So first of all, what is known as FSM? So FSMs are nothing but it's actually finite state machines. So they actually contains a finite number of states, and state transitions are there, and with the output logic. And FSM mainly depends upon the present state as well as the input whatever the VQ. So it also depends on some FSM depends on only present states also. So in that let's take we'll go further. So why we are using FSMs? So in day-to-day life, FSMs are everywhere. So let's take how systems require memories of past. So like so we are aware, like we are amazed, like how the digital circuits are remembering how the memory is actually playing the role. So that actually present as registers inside the FSMs. So mainly FSMs are used as in the daily life. Traffic lights actually working with FSM states. Inputs. So ATMs are working. Elevators. Protocol controllers also. So we'll go through the protocol and controls. They actually advanced topic. So actually mainly FSM controls sequence-based behavior. So let's take let's go through the ATM. So in ATM, what actually there is some sequence, right? First of all, you have to insert your ATM card. Then you have to then you have to select the options, whatever the banking systems you want. Then you have to enter the PIN, and then you will get the cash or whatever the output you want. So there is actually certain sequence is following. So every sequence, they are actually known as states. Like that, there are so many number of states we have. So this is actually the sequence we have to follow in. So if it follow the perfect sequence only, we will achieve the last output. So this is actually we are giving to the digital circuit think. Okay, the thinking mechanism we are giving. So that is actually an FSM. See, in the real life applications, we have the FSMs like in UART controller, we have a FSM. In SPI control, we have FSM. In I2C protocols, see, there are actually, let's take, it's a chip. So let's take it's an SOC. SOC is nothing but what? System on chip. System on chip. See, in system on chip, we have several IPs. Let's take, these are all IPs. So intellectual properties. So in every like integration of IPs, we will call it as an SOC. So let's take it is a camera module. Let's take it's a speaker. Let's take it's a flashlight. It's a CPU. There are so many IPs in an SOC. So each and everything has a particular mechanism, particular functionality. So let's take our chip, whatever the chip we have, it should communicate to the external physical things. So let's take we have USB input that should communicate, right? So for communication purpose, we are implementing some protocols. So like that, these are actually what we call SPI, I2C, UR. These are all for what serial communication protocols. So whatever the data processing inside the chip, that will be transmitted outside as a serial protocol. Serially, the data will transfer through these protocols. So protocol is nothing but what? Following some rules and regulations. Rules for data transmission. So they are nothing but protocols. So like this, chip will communicate to the external peripherals through these protocols. So that protocols will contain FSM. So that's why it's very important to learn FSM. See, there is also we have vending machines. We have recently in Amazon companies in warehouse also, warehouses of so many Amazon. So they are actually keeping the vending machines. Whatever the input we will like, let's take we have biscuits, let's take we have so many cool drinks are there. So we will select the first serial number. Then we will enter our cash. We'll pay the cash to the QR code. Then output automatically comes as the product we will get. So this thinking mechanism, how they are getting through the vending machine, through the FSM, we are giving that functionality. Even CPU control unit also has the FSM. See, so first of all, before going to FSM, we have to understand how the FSM actually structured. So first of all, FSM actually structured with state registers. So D flip-flops. So it will contain flip-flops and next state logic. So it contains some combination logics and the output logic. Both three will combinedly make an FSM. So in this manner, the FSM will be designed through coding or through any digital circuits. See, there are actually I said FSMs are mainly classified as Moore and Mealy. So what actually Moore? Moore machines actually depends only on the present states, whereas Mealy will depend both on present state as well as the present input. See, and again, why actually there are classified? So what's the functionality? What's the actually the main difference? Why we are using Moore? Moore will have some stable, so it will have like noise reductions. Sometimes circuits will prone to noise, so that noise and all less in Moore. Whereas coming to Mealy, the circuit will works faster since it contains less number of states. So we will see what are the states we have, why we are having states and all, what are states, what are the sequential logics and all. See, design steps. So we are actually following some steps to design the circuits. So first of all, we will understand the problem. What the problem we have? We are getting so many challenges in our life. So first of all, we have to understand what actually problem is. Then we have to draw some diagram. That is nothing but state diagram. Then we will go for stable state table. So whatever, if I give this input, which state I will go? Like that, we have to draw some table for our analyzation. Then we have to go. Then only we have to go for coding. There are so many coding styles. In that also we can pick some coding style. Then at last verifying the RTL. So these are the steps we are following. We should follow to design a perfect FSM. See, so we are going to detect 1001 sequence detector with a simple, just for understanding how the actually code will behave, how actually the structure of code will be. So detect 1001 in sequence, in serial stream. So we are giving the input 1001, not with the same, like 4 bits we are not giving. So we are giving the bits one by one, 1001. So whenever there are so many sequences are there. So let's take, if you want to design 1001 sequence, so let's take our input will be 100111000. In that sequence, how many times 1001 came? That actually the if what we are designing going to design this FSM. So it is going to detect how many times 1001 came. So and there are so many like so in Moore and Mealy also there are two FSM like FSMs are mainly classified into again two types like overlapping and non-overlapping again. So let's take this sequence 1001 1001. This is sort of what This is actually non-overlapping. So we are detecting the sequence separately. Let's take this example. See, if you consider this is as overlapping, so we can detect. So here we are detecting 1001, and whatever the detected bit we are using again. See, again we are detecting 1001. This is a sort of non-overlap. Like this is overlapping and this is non-overlapping. So non-overlapping and this is overlapping. Like this, like this type of sequence detectors we have. See, so before going to the code, we will understand how the FSM will look like for 1001 Moore. So 1001 Moore, we are going to detect it. So as I said before, first of all, we have to understand the problem, right? So our problem is what? Detecting 1001 sequence. Then we have to go for what? Then we have to draw the state transition diagram. State transition diagram. State diagram, simply we will call. So how the actually Moore will behave? See, so first of all, our main target is what? 1001 sequence detection. So let's take, so every FSM has initial state and as well as the final state. So initial state we will call it as idle. So idle state is nothing but initial state. Whereas the final state is called as detected state or whatever it may. You can give your own name. So let's take, I am taking S naught. So S naught as my initial state or ideal state. So Moore has, as I said before, each state, like state itself says the output for Moore. So see, so whenever we are doing the reset operation, so for this state, it will give the output as 0. So we are going for again what? We are giving, so we start giving our input. Whenever we give an input, so among this sequence, let's take if I am detecting from MSB onwards. So one is detected. So it will go to the first state, another state. Let's take S naught, but output not came here still. See, so this is the S naught with the state which detects 1. Up to here it will detect 1. After that, so we have for every state we have two outputs, like two transitions. So if we give 1, what it happens? If we give 0, what it happens? So see, so if I given 1 here, for from S0 to S1, we are going. I am giving 1 here. What if I give 0? 0 is nothing but what? It will stay. It will stay here only because S0 is the state of detecting 0. If we do the reset, so I am giving now 1. So since it detects 1, it going to next state which is able to detect 1. So again what? 1 0 I am giving. So 1 0. So we are having 1 0 state here. So it will detecting. So I will give, I am taking it as another state with output 0. Why I am taking output 0? Since it's detecting only two states only, two only. It's taking two variables only. Again we have to go for what? Again there are more states like 0 1 is there. That's why we are making it output as 0 only. First detect all the states. So again I'm giving 0. So let's take this output as the state as 3 and the output is 0 only. Why? Since it's not detected fully. So this is the state of 1 0 and this is the state of 1 0 0. And again what? And I am giving 1. So at last our mean state came, the last state, so which is able to detect 1001 sequence. So this is not a complete diagram. We have to further states are there. So here, right now we are in S1 state. For S1 state, we just given the output like you given the input as 0, then it going to the S2 state. What if you give the one input like if you give the input as 1, it will go to which state? So already one is detected. So if you give one means, so this state will be ignored and we have to search in such, we have to search one state. So where is one state here? So it is able. So here we have one state. So it will, if you give what are the, again if you give one here, it will go to the S1 state only. See again, so two are there like I said before. So if you give 1, what state it will go, and if you give 0, what state it will go. So these type of transitions are there. So see here in we are right now in S1 state. So here we given 0 and it goes to S3 state. We know that. What if you give 1 again? See 1 0 state we are there. What if we go 1? See, I am eliminating from MSB. So it's this bit is like eliminated. Is there any state with 0 1 state? No, right? So we have to eliminate that MSB also. Now we have 1. So there is a 1 state. See, this is the 1 state here. Like this, we have to check for both 0 and 1 transitions. See, again we are in 1 0 0 state. So we given 1, it goes to the final state which detected 1 0 0. What if we give 1 0 0? So since we are here 1 0 0 state, what if we give 0 again? If you give 1 means it's going to the new state. What if we give 0? Start eliminating from MSB. Is there any state which has 0 0 0? No, right? Again start eliminating. Is there any state with 0 0? No, right? But there is a state with 0. So we have to go and we have to give here. Similarly, we are right now in S4 state. What if we give, since we are in 1001, what if we give 0, 100, what if we give 1? So we have to say the next states also, right? So we have to give both 0 and 1 for this S0. Then how, or like which state it goes, we have to check again. See, as I said before, start eliminating from MSB. Is there any state which is detecting 0, 0, 1, 0? No, right? Then again eliminate them. So is there any state with 0, 1, 0? No. Yeah, but there is a state which is detecting 1, 0. But since we are following non-overlapping, since we are following the non-overlapping technique, we should not take this also. Only the next, last new bit we have to take. See, where is the state of 0 detection? So there is a state with 0 detection here. So initial state. So this is the initial state which is detecting 0. Like that. Again, there is a, what if you give 1 if you are in 1001 state? So eliminate for MSB onwards. There is no states which contain 0011. Again eliminate. There is no state with 011. Again eliminate. There is no state with 11. Again eliminate. There is a state with 1. So again we will go to here. If we give the 1 input. Like this we have to draw the state diagram of more emissions. See, so here we have mission. So here we have the sequence. So here we have the state diagram. By seeing the state diagram, simply we can write the logic. Let me explain the logic here. See, so first of all, as you know, first of all, we have to declare the module with our own name. Here, as I said before, the FSMs works, they are actually contain sequential logic, combinational logics, and the output logic. So since they are having the sequential logic, we have to consider the clock. And we have the reset operation for initializing the circuit. And we have data in. Based upon data in only, right? It's detecting. So and again sequence detected. This is the output. So if the sequence is detected, this will be driven with 1. Like that we are going. Now the actually game comes here. So here we have to declare the parameters. So parameters are nothing but what? See, so how many states totally we got? 1, 2, 3, 4, 5. 5 states we totally got. So how you declare the number with 5, how many bits we can declare the 5? We need, let's take 101 is a representation of binary, like, so minimum 3 bits are required to detect to have 5 states. That's why we are parameterizing it 2 down to 0. So then we started declaring the states. So S0 3 down to, like, it's like 0 0 0, S1 like this, S4 up to, we have to declare the parameters. So actually they are the values. So they are actually the values which we are just representing the each state. Then the main game comes here. Here we have to declare the register. So 2 registers we have to declare. So current state as well as the next state. So reg. So this is actually for storing purpose. As I said before, FSMs have memory elements also, right? So that's why we are declaring register. It will, if you fabricate this, it will invokes D flip-flops. So for actually we have current state and the next state. So current state is nothing but just don't confuse. So if you are in S0, if you give the input 1, it will go to S1. So now the current state is S0. And the next state is what? S1. Like that, for that purpose, we declared the register current state and next state. Now this is actually up to here declaration part. So declaration part. Now the game comes here. See, here actually the combination logic. And sorry, this is the actually sequential logic. And here the combination logic. And here the output. As I said before, the FSM contains sequential, combination, and output logics. See, the sequential logic contains what? Always at the rate of passage of the clock, we are triggering the circuit at clock only, like positive to the clock only. And at negative edge, we are doing the reset, since it is active low reset. So industry following active low reset only. See, if we do the reset operation, the current state is assigned with S0, or else the current state is assigned with the next state. This is the actually simple sequential logic. See, again we are going for the combination logic. So combination logic is nothing but if you give the input 1, what state it will go? If you give the input 0, what state it will go? That logic we had right. See, we are using case statement for simplification, like for visibility, good visibility, we are using case, and here we are using ternary operator also. Ternary operator. It's simply like what? Ternary operators are nothing but if else. So if else. So I think the ternary operators. So if data is in 1, if it is true is nothing but if condition. If it is 1, it will goes to S1 state. If it is false is nothing but we are using a colon. So it will go to S0 state. See, as according to the diagram, the current state and this case state is going on. So right now I am in S0 state. If I give 1 as input, where I am going? So if I give the input as, so here the data in is 1 means, so I am going to the S1 state. See, and if I give the input as 0, so if I give input as 0, what state I am going? I am staying in the S0 state itself. Like that we have to write all the transitions. And this is simple combination logic. And at last we are going for again what? Output logic. So as I said before, Moore depends only on the present state. Whenever if you come to the S0 state, S4 state, output will become S1. That's it. It won't depends upon the input. Whenever it comes to the S4 state, it will detect, like it will throw the output as 1. Like that logic we have to write. That is actually Moore. See, whenever the current state is S4, whenever the current state is S4, the output should be 1. 1 is assigned to the sequence detected. So this is the output, right? We declared in the module. So that 1 is assigned to the sequence detector. So it depends only on the state. Moore depends only on the state. So this is the styling. This is the way of code styling of the Moore of simple 1001 detection. So now we will go for Mealy. So Mealy as actually is also like same. Only so before going to the like Moore, like Mealy, now we will discuss the test bench, how the test bench actually looks like for this. See, so we have to write our own module name something. So whatever the inputs we have to declare as reg, and output we have to declare as wire. And we have to instantiate the design. Instantiating. As I said before, instantiation. So instantiation is nothing but what? You have to map whatever the registers and wire you declared in the TP to the RTL. So that's mapping is nothing but what are the inputs we are generating that should go to the RTL through the instantiation only. So you have to instantiate. Then we have to initializing the clock. Then we are generating the clock. So how this clock actually looks like this. So the time period of each clock is what? Since it is toggling from for every 5 seconds, for every five time period, not I'm not saying any time units. So just take as units. So here for every 5 units is toggling. So it's 5 and it is 5. So totally the 10 time units is the clock period of our circuit. 1 second. See, this is the 10 time period of our circuit. And so we are taking a simple task where we are driving our inputs at a clock edge, at positive clock edge. So whatever, when you call this task and provide the input, So that input will be assigned to the D in, whatever we declared. Okay. Like this, we are going to writing a small task that should trigger, that should give the input exactly at the positive edge. See, it's actually no need, but actually for reusable purpose, we are actually doing this one. Directly you can write here, at the rate of positive, at the rate of negative, you can drive your own inputs directly to the D in. And in the, here the runtime begins. So runtime actually, we are giving our inputs to the RTL. See, we are first of all, since it's actually active low reset, we are making it as 0. And we are initializing our D input also as 0. After some delay, after 20 delay, we are making it as high. Here, after making reset as high, the operation begins. We are start driving our inputs. I am driving 1001. At this data, at this time period, our output should go high. That only you have to check in the waveforms. So this is a simple TP for 1001 Moore RTL. So we'll go for Mealy also. See, before going for Mealy, let me explain the difference of state diagrams. So as I said before, so first of all, we have to understand the problem, then state diagram plus state diagram, then Verilog coding we have to do. So this is the steps we have to follow for making any sequence detection. This is very simple. But if you are working with the projects, so we have so many state transitions. We have like combinations of FSMs out there. Not only single FSM, combination of FSM. We have to integrate so many FSM in a single module. Like that we have again. So this is basic understanding. You have to understand the basic, then only we will work on complex things. So we are going to plan some many projects and major projects, fully working on FSMs only. So just understand it perfectly. See, here we are going to detect what 1001 only again. But if it's a Mealy style. So Mealy actually has the output. Now let's take S0 is there. So S0 is a state which is going to detect what? Just it's actually a reset state. So if you do the reset, it will go to the S0. Like it's like ideal state. So whenever I give input as 1, so here the output actually the diagram look like this. So whenever give the 1 output, we have the output instantly here only. Not it depends both on state as well as inputs, as I said before, Mealy. So that's why we are taking output here. See, as 1, whenever give the input as 1, it will go to the S1 state, which is capable of detecting 1. Whenever if you give the input as 0, it is capable of detecting what again? 10 state. And again, when we will give the input as 0 again, it is the state which is capable of detecting what? 100. See, after going to, like, it's detected up to 3 bits. Now it is able to detect again what? It should detect again 1, right? So whenever it is going to detect 1, it will go to the reset here. So see, whenever it detects 1, the output will be high. So here, when compared to the Moore, the number of states are less. That's why the complexity. Let me complete this diagram, then I will explain what actually happening between Mealy and Moore. See, so here I given 1 and I am getting output as 1. So it depends upon the state. Here the state is S3 and the input is 1, then the output will be 1. So here what? It depends upon both state as well as the current input. So actually, but coming to the Mealy, like Moore, it only like whenever the state is S4, the output should be 1. It won't depends upon 1 or 0 inputs. It won't depend upon inputs. Just it depends upon the current state. But here the Mealy will depends both on the current state as well as the input we provided. So that's the thing. See, we will complete this diagram. See, we are in right now we are in S1. So it is capable of detecting 1. So what if we give 1 0? If we give 1 0, it will go to the S2 state. What if we give 1 1 state? Start eliminating for MSB. So we have 1. So it is going to the same state. Again, now we are in S0 state, 1 0 state. If we give the input as 0, it goes to the new state. What if we give the input as 1? Eliminate from MSB. 0 1 is not there. 1 is there again. So it will go to the 1 1 state again. Now we are in S100 state. What if we give 0? Start eliminating from MSB. 0 0 not there. 0 0 is not there. 0 is there. It will go to here again. But output is 0 only. See, this is the simple FSM of Mealy. So based on this FSM state diagram, we are going to have to write the code for here. See what happens here. The number of states are in Mure. The states are 5. Coming to Mealy, the states are 4 only. So automatically, wait a while. Yeah, fine. So here the number of states are 5 and here the number of states are 4. That's why the circuit complexity of more is more. So automatically it need more registers, it need more circuit. Since it's more, like it's need more circuit, automatically the fast is less. So that's why the Murray is the maybe the fastness is less, but it has a higher security. Coming to Mealy, what? So it has less number of states first. That's why the fastness is also more. Less number of states, fastness is there, and thus since it has less number of states, automatically the circuit complexity is also less. But Mealy is not preferable when comparedly because some glitches it prone to some glitches, some noise will be added in Mealy. Though that's why the mostly in the industry Moore is preferred. And see, so this is similar to before code Moore only like declarations and states and sequential logic and combination logic. Only the difference between the Mealy and Moore coding style is here. See, as I said before, if you go, it only depends upon the current state. Whenever the current state is S4, it will give the output as 1. But here, whenever the current state is 100, like 100 is nothing but this one only, like S3 state. Whenever the 100, it goes to the 100 state, and whenever the input is high, so whenever the DIN is high, DIN is nothing but what? So 1. Whenever the input is 1, then the sequence detection happens. So then the output will be assigned to 1 or else 0. So see, if else is there. So and here if you see the if statement, so it should be the state, it should be the S3 state and it should be the data in should be 1. So it depends on both input as well as the current state. So that's the main difference between the Moore and Mealy. So like this we are going to code the Mealy style coding. So as you know, TV is nothing but simply so writing your declaration of a reg, like inputs as reg, outputs as wire, and our instantiation, and then clock generation, and then some task, it's your choice, and then initialize and like runtime we have to assign, we have to make a reset, and then we have to make reset as high, and we have to give the main inputs that are given. Based on your inputs only, we are going to detect, we are going to analyze the waveforms. So and I'm terminating the waveform, like terminating the simulation at after 50 delay and simply like this the FSM coding will be. That's it. So like this we have the FSM coding styles. So the main I will give the assignments like so many combinations. So your main assignments you will work on both the overlapping as well as non-overlapping. So first draw the state transition. So draw the state transition diagram, then proceed for Verilog coding. So simple, like take so many, I will provide some questions, but you practice more. So the like we are working with 1001 sequence. You will take 101 or 100 or 111 or 100111. Take as much as your sequence, just try to practice and just try to analyze the waveforms. So the more practice you did, the more analysis you will get. So some are confusing at blocking and non-blocking. So here blocking will execute it will exactly updates it here. What whenever you are updating, it's exactly updates here. Coming to non-blocking, it will updates the previous value. Just go through it once again. Don't confuse. And see, so the main comparison is what? So Moore output depends only on the current state, and there are more number of states, and stable output will be there. And coming to the Mealy, output depends on present state as well as the present input, and fewer number of states and faster response, like that. And see, What are the advantages of FSM? So what is the, like we are learning FSM, but why we are using, what are the advantages we have to know, right? So we have to predict the behavior easily and easy to debugging and structured design, as you know. So if you are giving some brain to any chip, that chip should detect or that chip to able to think all the corner conditions also. Like that we have to design like that. That's the main advantage. And reusable modules. So here we have using so many modules. So this FSM can be used in other design. Like that, if whatever the FSM you are designing and you are coding, that won't be misused, like that won't be wasted. So we can use it in another design, we can make it instantiation in another design, and we can reuse it again. Like that. So common coding mistakes you will do in FSM sort. So you will forget the default case. So in the combination logic, we have to mention the default case. That's the common mistakes most students do. So just try to avoid that one. And you will mix the non-blocking with blocking. So if you are working, like as I said before, so there are how many logics? Sequential logic is there, com logic is there, and at last output logic is there. So try to mention here non-blocking only in sequential, and in com logic and output logic try to mention blocking only. So these are the common mistakes we are going to, like most students will do. So try to avoid them. And not separating combination and sequential. So they will mix with this combination and sequential. So don't try to mix them. Try it separately. Then only proper readability will be there, and only perfect observation. If you throw any bug, you can easily debug them. So follow the structured coding, like follow the perfect indentations, then you can easily be a good coder. Then, so what's the verification strategy? As I said before, apply test patterns. So how you, so as many as so in the test bench I just given 1001 like that. So you can like you can give your more inputs, like so many, like continuously zeros, continuously ones, continuously 1010 like that. Try to give as much as stimulus, try to observe the waveforms. So based on your test patterns only, the RTL will be verified perfectly. And check each transition whether it is that state is transition, that state is going to change perfectly or not. You have to observe and check output timings, when that at what time the output is going to be updated. So sometimes the output is updated before what you assumed. So that not should be done, because of non-blocking only the timing issues will come. So just check it once again. And so these are the main interview questions mostly will ask. What's the main difference between Mealy and Murray? Why separate new state logics we are using, and which is faster among them? So these are the common questions we are going to have between Mealy and Murray. And see, so we are going to wind up the session. So FSMs are actually the combination of state registers and as well as the combination logics we have. So it is used to in every digital controller. Almost every digital controlling circuit or ICs we have FSMs, and they're mainly classified as Moore and Mealy. So these are the main things we have to understand about Mealy and Moore. So that's the thing. So that's the student. Just try to practice as much as you can. So I'm going to share the this video again to you. So this like this you have to assume, like I will provide the assignments, just try to work on them. And mostly uh, so Thursday onwards we have to start some mini project. So the title and all we will discuss on next session. The session dates mostly the next session on Thursday only. Thursday evening we will meet. So we start going to work on the small mini project. So deadline like mostly is like 1 week or like that. So try to practice as much as FSMs and counters also. I provided in the ELAN like LMS, I provided some extra Verilog codes. So based on counters, just try to work on them. So that's the thing. Hope you all enjoyed the session today. Like almost 24, 23 students are there. That's it, guys. If you have any doubts, you can proceed, or we will wind up the session today.